Beneath the ocean's surface, hydrothermal vents host ecosystems thriving without sunlight. In this video, you'll learn how vents form, the chemosynthetic processes powering life, unique adaptations of vent organisms, and why vents matter for science, industry, and conservation. Where vents form and their environment. Hydrothermal vents form along mid-ocean ridges and volcanic arcs where seawater penetrates fractured ocean crust, heats to 250 to 400 degrees Celsius, and rises back to the seafloor. Discovered in 1977 near the Galapagos Rift, vents create mineral-rich plumes and chimney structures. Black smokers deposit iron, copper, and sulfide minerals at temperatures often exceeding 350 degrees Celsius. Despite extreme pressure and darkness, vent fields can span meters to kilometers and host dense biological communities. Key physical parameters include high hydrostatic pressure, up to 400 atmospheres at 4,000 meters depth, steep chemical gradients, and rapid temperature changes over centimeters. These environmental gradients provide the energy and raw materials that sustain chemosynthetic ecosystems. Chemosynthesis, life without sunlight. At vents, primary production is driven by chemosynthesis rather than photosynthesis. Chemolypho autotrophic microbes oxidize reduced chemicals, hydrogen sulfide, H2S, methane, CH4, hydrogen, and fix CO2 via pathways like the Calvin cycle or reverse TCA. For example, sulfide oxidizing bacteria gain approximately 794 kilojoules per mole from oxidizing H2S with O2, powering carbon fixation. These microbes either form free-living mats or live inside animal hosts. Giant tube worms, Ristia pachyptila, harbor sulfur-oxidizing endosymbionts in a trophosome, supplying up to 80% of the worm's carbon. Primary production rates at vents can reach several grams of carbon per square meter per day, supporting dense, fast-growing assemblages despite total deep-sea oligotrophy. Applications: origins, biotechnology, and minerals. Hydrothermal vent research has practical and theoretical implications. The 2000 Lost City field on the mid-Atlantic ridge, 40 to 90 degrees Celsius, produces abundant hydrogen, up to micromolar to millimolar levels locally, lending support to alkaline hydrothermal origin of life models by offering steady proton gradients and chemical reactants. Vents are also targets for biotechnology. Thermostable enzymes and novel antibiotics have been isolated from vent microbes. For instance, vent-derived protease and polymerases function at 70 to 100 degrees Celsius. Industrial interest includes seafloor massive sulfide deposits, with copper grades often exceeding 2 to 5%, richer than many land ores, driving deep-sea mining proposals and raising urgent conservation concerns about biodiversity loss and ecosystem services. Exploration, policy, and conservation. Protecting vent ecosystems requires technology, monitoring, and international policy. To date, scientists have documented over 500 hydrothermal vent fields worldwide, though many remain undiscovered in remote basins. Vent lifespans vary. Black smoker chimneys can be active for years to decades. Whole fields may persist for centuries following volcanic events. Exploration relies on remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, capable of reaching over 4,000 meters and deploying in situ mass spectrometers, temperature probes, and microbial samplers. Legal frameworks like the International Seabed Authority regulate mineral extraction beyond national waters. But balancing scientific value, bioprospecting, and mining interests is an urgent multidisciplinary challenge. Hydrothermal vents are dynamic, chemically rich oases that sustain life through chemosynthesis, reveal possible pathways for life's origins, and offer biotechnological and mineral resources. Protecting them requires better exploration, technology, and international policy to balance scientific discovery, commercial interest, and biodiversity conservation.